Alright, for today we are looking at the derivative of the exponential function, or exponential functions. Up to this point we've seen functions that are polynomials, so something like x squared plus 3x plus 2 would be an example of what we've done so far. And today we're going to look at exponential functions, so some examples of those um, are something like 2 to the x, 10 to the x, and we'll also look at e to the x. And there's something special about that derivative, which we will get into later on. First things first, let's just look at sketching the derivative. This is some generic exponential function, which is just marked a to the x. We're going to sketch a rough estimate of the derivative of a to the x here. So if we look at the slopes of the tangent lines, so over here where we have very negative values for x, our slopes are going to be positive, but very, very shallow, not very steep at all. And so we can mark something small there. And as we see, as we get progressively further or larger and larger values for x, the slopes are going to increase. So our derivatives also have to be increasing. So our function is going to look something like this, which is very similar to the exponential function if you notice there. And we'll see that when we find the actual rule for derivatives of exponential functions. But first off, let's see if we can find this algebraically. So let's use the definition of the derivative. So the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we evaluate this for the function a to the x, we have the limit as h approaches 0 of a to the x plus h minus a to the x all over h. So we took x plus h, plugged it into our function wherever we saw an x. In our numerator here, we can simplify a little bit. So the limit as h approaches 0, a to the x plus h can be written as a to the x times a to the h. So if we're adding exponents, it's the same thing as multiplying two numbers with the same base. And then we have minus a to the x all over h. Now the numerator can be simplified a little bit more. If you look here, we have an a to the x in both of those terms. So we can factor out an a to the x. So the limit as h approaches 0 of a to the x times a to the h minus 1 all over h. And at this point, we have this a to the x that we're multiplying by out front. When we evaluate the limit, we're going to be plugging in 0 for h. Since a to the x doesn't have an h in it, it's not going to be impacting anything in terms of evaluating the limit. So we can actually think of it as a constant or a type of constant and pull it out because it's not going to impact our limit. So we can rewrite this as a to the x times the limit as h approaches 0 of a to the h minus 1 all over h. And now at this point, if we plug in 0 for h, we get a to the 0 minus 1, which is 1 minus 1 all over 0. So 1 minus 1 over 0 gives us 0 over 0, which we don't want for our functions. We would have to do some algebra to factor or to simplify that so we can plug in our h value and not get something over 0. But unfortunately, we don't have the skills right now or the tools right now to be able to simplify that. So we're stuck with this piece here. And if we were in class, or I was in class, we would be able to explore this and we do a little activity with it. And we will do that on Monday just to go through it quick. But you are going to have to believe me and follow blindly that when I say that the limit as h approaches 0 of a to the h minus 1 all over h is the same as the natural log of a. So our rule for exponential functions is the derivative. If we have some function a to the x, the derivative is a to the x times the natural log of a. So let's run through a few examples here. Nope, let's not run through a few examples. Let's wait a second. Let's look at the special value here quick. So when does the natural log of a equal 1? And so that happens when we have the natural log of e. So we talked about natural log and e being inverses of each other, so they cancel each other out. So the derivative of e to the x would be e to the x times the natural log of e, and we just said the natural log of e was 1. So what works out really nicely is that the derivative of e to the x is just e to the x. Okay. So this is the one function that is its own derivative. How cool is that? All right, now we get to these examples here. And so what I would recommend doing is you can pause the video now and you can try some of these yourself, or you can let me go through a couple of these with you, and then you can try the last two or three on your own. So our rule for derivatives of exponential functions, say we have some base a to the x power, our rule is a to the x times the natural log of a. So in this case, when we have the function y equals 5 to the x, the derivative is 5 to the x times the natural log of 5. And that's it. We're obviously going to run into some more complex exponential functions. So here we have some 3, a constant multiplied by 2 to the x. Remember, when we're evaluating derivatives, we can take that 3 out and disregard it while we take the derivative. And the derivative of 2 to the x is 2 to the x times the natural log of 2. And we don't need to simplify that. That's as far as we need to go for that answer. So once again, you can pause the video at any time and go through these and solve them on your own. So I'm going to go ahead and get to this last one, or the last two here. Our third function is y equals e to the x plus e squared. Before we evaluate the derivative, so think about this. E to the x is obviously a function. E squared, so e is a number, and when we raise a number to the second power, we're going to still have a number. Okay? And so when we take the derivative of a constant value or the derivative of e squared, we're going to end up getting 0, and the derivative of e to the x is just e to the x. And the last one here, 5 times e to the x. Once again, we have a constant multiplied by e to the x. We can pull that constant out before we evaluate our derivative, and the derivative of e to the x is just e to the x. So pretty nicely, the derivative of 5e to the x is 5e to the x. A few more complicated ones. I would like you to pause the video now and go through and solve these ones on your own. All right, so our first function here, so f of x equals 4 to the x plus x to the fourth, will involve both the exponential rule or exponential function derivative rule that we have for today and our power rule that we've been working on the last couple days before this. So if we look at 4 to the x first, the derivative of 4 to the x is 4 to the x times the natural log of 4. And our derivative of x to the fourth, if we so we think about multiplying that exponent down to the front, so 4x, and then subtract 1 from our exponent, to get 4x cubed. G of x here, we have a couple different rules again that we're going to be using, but let's rewrite this so we don't have a square root of x. We can rewrite it as an exponent first. So it's 6e to the x plus x to the 1/2 plus 6. So the derivative of 6e to the x, 6 is a constant, so we can pull that out, and the derivative of e to the x is just e to the x. So the derivative of 6e to the x is just 6e to the x. Derivative of x to the 1/2, remember we're multiplying 1/2 out in front, and then subtracting 1 from our exponent to give us 1/2 x to the negative 1/2. And our last term is 6. The derivative of a constant is always 0, so we lose that term there. We need to simplify this last equation, though. We don't want to have any negative exponents. So 6e to the x plus 1 over 2 root x. The last term here, h of x equals e to the x plus 1 over 3. Right now we have some rational function we want to change or rewrite this so we can take the derivative. So remember, we can multiply, or excuse me, not multiply, we can divide the denominator by both the terms in the numerator to simplify this. So e to the x over 3 plus 1 over 3. And we can simplify this even further. E to the x over 3 is the same thing as e to the x times 1/3. So that should be a little bit nicer for us when we end up taking our derivative. So the derivative of e to the x is just e to the x. And 1/3, that constant out in front, we can bring along with it. And the derivative of 1/3 is 0. So that function is nice. A nice derivative for us, 1/3 e to the x. I'd like you to take a second, look over these two problems here, and do the derivatives. If we look at our first one, e to the pi plus pi to the e, pi is a number and e is a number, so e to the pi power is just another constant, as is pi to the e power. So both of those will be numbers, When we take the derivative, we get 0. It's the second one here where we have to use our rules. Pi to the x power is going to be our exponential rule. So pi to the x times the natural log of our base, which is pi, plus x to the pi is going to be our power rule. So we multiply by our exponent out front, so pi times x, and subtract 1 from our exponent. So the derivative of pi to the x plus x to the pi is pi to the x times the natural log of pi plus pi times x to the pi minus 1. And the last one we'll look at here is just an application. It says that since January 1st, 1960, the population of Slim Chance has been described by the formula P of t equals 35,000 times 0.98 to the t power, where P is the population of the city t years after the start of 1960. At what rate was the population changing on January 1st, 1983? So if we're looking for a rate here, this means we're looking for the derivative, and more specifically, we're looking for the instantaneous rate of change in 1983 for the population. So let's start with finding the derivative here of our equation. 35,000, we can think of this as being a constant. Okay, so we don't have to evaluate our derivative with 35,000 in there. What we're really looking at is 0.98 to the t power, and that's an exponential function. So our rule says we have 0.98 to the t times the natural log of 0.98. So there's our derivative function for that population formula. And we need to evaluate this in 1983, which is 23 years after 1960. So our t value should be 23. So you can plug in 23 for t, and we get 35,000 times 0.98 to the 23rd power times the natural log of 0.98. And you can evaluate this function and figure out what the rate of change is for the population. I'm not going to do that. My calculator's a little bit slower than you, so I'll let you go. Homework for the weekend on section 3.2. Come with questions on Monday. I'll answer those at the beginning of class, and have a good weekend.